I got this pill. I think it's going to lower the amount of time you have the common cold. Stay with me now, guys, okay? You got time. It's going to lower the amount of time you have the common cold. How can we prove that it is, in fact, better? Now, we set up the experiments before. Today, we're going to learn the math behind it. Okay? All right, number one, did you draw a picture? Yes. Should have. Remember, we always draw a picture on this. Okay, we have random assignment. You've got your treatment group. This is the guys getting the pill. This is the guys getting the placebo. Did you put and define your response variable? You should have. The response variable in this is you know, we're going to ask them how many days till you got better. So it's going to be that we're going to look at the average time it takes to get better using the pill, okay, versus the placebo. So that's what we're going to be analyzing when we're done. All right, randomization. All right, we have 61. I hope none of you got rid of that 61st person. Third period, I got people getting rid of. No, the more the merrier. We don't have to have the same amount in each group, remember? That's not necessary here. A couple of ways you could have done this. Put all 61 names in a hat. You know, first 30 I pick get the treatment, the next 31 don't. Something like that's fine. Assign everybody a number between 0, 1, and 61. Go to my digit chart, looking at 2 digits at a time, ignoring repeats and numbers outside the range. First 31 I pick go to this group, the next 30 I go to this group. Okay, something like that is fine. You have to have a random mechanism. Now, replication. You noticed I did keep those groups the same. Now, remember what the goal of randomization is. We want to create 2 environments that start out very much the same. Not a lot of variation in these groups. The people about the same number of old and young, the same healthy and not healthy. That's what randomization does for us. Creates homogeneous environments. Okay? Now remember, if we had one lurking variable that was too big, we used block. You see? I don't even know what you said, but I'm going to pretend it was blocking. Remember blocking? You know, we take out boys and girls and then do the experiments. Okay? That was a design that we talked about. But in this case, we'll just put them into the 2 groups. So, to reduce the chance variation in my treatment groups, we're going to make sure we have 30 and 31 people in the groups. Okay? Now, if we had started with 500, I wouldn't have required that. Okay? Just let it fall where it falls. That's great randomization. Yeah.
So I was just going to ask how big the sample has to be to do that.
Well, you know, we've been seeing this magic number 40, right? That's kind of a cool number, so maybe more than 40 might be a good place to start. So maybe at least 100 total, so we make sure we get 40 in each group. Might be good. Okay, and then finally control. I hope you use the word double blinding. Remember, blinding, you probably make sure the pill looks exactly the same. That's blinding. The person doesn't know whether they're getting the treatment or the placebo. Double blinding, I think the person may be asking the questions, how many days did it take you to get better? I don't know which pill you got, right? So I don't subtly, you know, try to lead you in one direction or the other. Okay, you might have done some more things like at just a certain time of year or follow them or, you know, some other little things in there to make sure that the groups are treated the same. Okay? Yeah.
In randomization, I just want to make sure, because I remember you said there was a specific way not to randomize, so I want to make sure that what I had wasn't.
Okay, what you do?
When you assign them all their number, and then when you randomly select them with the calculator,
okay,
you go every other one going into.
You could do it either way. I mean, you could say the first 31 numbers that come up go here, the next 30 go here, or every other one. That's fine.
Okay.
That works. Just the key thing is you don't want to be saying it has to be those random numbers that come up that put them in those, not you. Okay. Yeah.
In control, do you want us to mention like that each pill like would look and smell and taste the same?
Yeah, I said look, but yeah, all that stuff is good too. Yeah. All right, so now that's how we design the experiment. Let's fast forward and get some results. Okay. Let's say in our treatment group. Now I want to describe it. You know, make sure you have a subscript that really describes what's going on. It's going to get crazy over here when we start doing our hypothesis tests and stuff. So I would do subscript T. Don't do 1s and 2s or whatever. Make sure you know what you're talking about. So, you know what? Our treatment group, they were better on average in about 4.2 days. Their sample standard deviation of the treatment group was about 1.2 days. And and let's say these guys had the sample size of 31. Now in our placebo group, they got better on average in about 5.5 days. Their standard deviation was about 1.5 days, and let's say that's the group that only had 30 people in it. So here's the question. Looks pretty good in my sample, right? People are getting better quicker in my sample. But is this a big enough difference? Is 1.3 days beyond the element of chance? There's no way I could get a difference like that if the pill wasn't doing anything. Okay, p-value. What are the chances? Is that likely? Could that happen? Or is that so unlikely we know the pill had to work for us? Okay, so what's the math behind solving this problem to see if we can put this pill on the market and we know it's going to cure colds quicker? All right, first things first. One of the differences we have here, I'm going to talk about the sampling distribution in a second. If we subtract these two, I've got negative 1.3. That is one element of this sampling distribution that we're looking at now. Okay? Now the sampling distribution, remember how big this is, it's every possible sample of 31 people you can give it to, every possible sample of 30 that you can give it to, and all the possible differences we could get. Okay, we got 1 point, negative 1 point, that's in there somewhere, and all the other possibilities are in there too. It's infinite, it's huge, right? Okay, here is the formula. Here is the formula that determines how spread out those differences of x bars will be. Okay? This is on your green sheets. Go find it, page 5. This is not one we have to memorize. It's on page 5. It says the difference of sample means, right? And the standard deviation of all those difference of sample means. And that's the formula that we're going to use to figure out how spread out all of these differences are. Now, this thing, like, what the heck? Where'd they get that from? It shouldn't freak you out that much. Do you remember way back in the day when we were doing linear transformation, and we said, what if we have two groups of numbers, and I want to create a new distribution that adds them together? Remember, you could just add the means. But do you remember what you had to do to find the new standard deviation? You had to... It was, remember the term add the variances? Whether you were adding or subtracting, combining, Braden, yes you do. Add the variances if the distributions were independent or not. Anyway, that's what we're doing here. We're taking two groups of numbers, we're subtracting them, okay? We're adding the variances, okay, to find the new standard deviation. Yeah.
I thought you don't want us using 1 and 2s.
That's just the formula. Okay. Now, once we get to a specific problem, I want you to put the subscript in that makes sense. Okay. So that's our new standard deviation of this distribution. Okay. So let's start from the beginning. How would we do a hypothesis test to see if we have statistically significant evidence to say this new medicine works? Okay. All right, we have two different samples now. We're going to give a bunch of people the treatment. We're going to give a bunch of people the placebo. So there's two means that I'm interested in this problem, and we define them both. Okay, this is the first time we've had two different means we're comparing at the same time. So U sub t would be the real mean number of days that your cold is going to last, given the new medication. Okay. The true average number of days your cold is going to last given the medication. Now, we got the same thing here, except now we're using placebo. You can go ahead and use dittos. Let's use dittos here to save some time. So the true mean number of days it'll take for your cold to get better, and then write the word in with the placebo. Okay? So we've defined these two groups that we're looking at in this problem. So going into this experiment, what do you think our null hypothesis is going to be? What are we going to assume to be true? What? No difference. I like the way he said that. Okay. He said there's not going to be any difference. Your new pill isn't going to be any different than the old. No difference. I'm going to write down what you said. You said no difference. So I'm going to say, is this okay if I say that mu sub t minus mu sub p is going to be equal to what? If there's no difference. 0. There's no difference. Now, another way to write it, I don't want you to write it this way, but you'll see it a lot, and you're going to like it a lot, but saying that mu sub t is the same as mu sub p. That's saying the same thing. You'll see it that way. It's kind of important we write it this way, and you'll see why when we get to the formula later, but that's really what we're saying. Yeah.
So if we wrote it like either way, we would mark that point.
Well, no. All right. What's our alternate going to be now? Obviously, we're trying to prove that this pill's great. Careful now. How are you? There. Yeah, you're scared. I say, be careful. How are you gonna do the sign on this? You got a 50-50 chance if you're guessing. What do you got, Monica?
Greater than?
No! Let's think about this now. You got to be careful with time. You got to be careful with time.
Oh, listen.
It's better. Yeah, the better is less, right?
Yeah.
It's like running a race, right? Oh, the better is less. So you got to be careful with that. So yeah, I actually want the treatment time to be less. I mean, I'm going to have the cold less, right? Be careful about that. I guess the other way, treatment is less. I know. It's probably a nicer way to look at it. Time is tricky. Time is tricky. I'm working with time. Okay, so you don't have to write them both. Please don't. Just pick one of them. I prefer this, and you'll see why in a second. Now remember, we got a difference of 1.3. Is that a big deal? Or could that happen a lot of times when you would go through this experiment? All right, level of significance, everything's the same here. Now, here's the deal up here. We're going to do the same thing we've done before, but we've got to do it twice. We have two different populations of interest. We've got the group getting the treatment, and we've got the group getting the placebo. Okay? So how each one has to be checked separately, and they all have to work. So for example, the first one, was there a simple random sample? Were these drawn in creating simple random samples? Here's our new formula. We want to know if that's the right one to use. Yes. What do we have? 31 here. 31 is less than 10% of all the people that could get the treatment. 30 is less than all the people who could get the placebo. So you're doing the same exact thing, but you're checking both populations of interest. Will the sampling distribution of x bar t minus x bar p be normal? If I got all these different differences here, would they create a normal distribution? What would we do in this problem? Well, they didn't give me the actual data, did they? So I would have to say, because the sample size is 31, we have to assume the population distribution is normal. Do the sample size of 30, assume the population distribution is normal. Now, if they actually gave me the numbers, I would do two sets of box plots and analyze them both. Okay. We're going to use a t-distribution. Yep, population standard deviation of the treatment, unknown. Population standard deviation of the placebo group, unknown. And finally, the last one. Remember when we did match pairs? Now remember match pairs, we had two groups, but there was a one-to-one relationship. I wanted to compare the same person against the same person. These are different people in these groups. There's no one-to-one comparison. So we're not doing a match pair. We're doing a two-sample test because they were independently drawn. Those two samples are independent of each other. It's not the same person in both groups, like the before and after test. Or there's not two plots that are exactly the same, so we keep them together. Okay, these people are totally separate. They're totally independent groups, chosen independently. I'm going to give them different treatments. Okay, and like I said, you don't even have to do 5 and 5. That's just, were they independently drawn samples, or are those samples dependent on each other? Okay, so it's the same assumptions we've been doing. You just got to do them twice. Yeah.
Assumption number 2, what we can check.
Okay, so is this the right formula or not? Same idea that the samples can't be too big compared to their population size. So same thing here. The sample's less than 10% of the population size, and so you'd say 31 is less than all the people, 10% of all the people that could get the treatment. 30, because that was the sample size over here, is less than 10% of all. Yeah.
For assumption 2, under the square root, is that standard deviation squared?
Yeah, it's not standard deviation squared, it's called the variance. Remember? Squared variance? I told you a long time ago that we actually would use variance down the road. Well, that's our today. Okay, all right, we're going to do, go find out how many standard deviations that 1.3 is. So this is our test statistic. Okay, so what we're really interested in, the top here is that negative 1.3. How big a deal is that negative 1.3? Well, let's see how many standard deviations 1.3 is. So down here is the formula for what a standard deviation is in a now you see over here mu1 minus mu2, that's just 0. That's why I like to write it like this. You see this, you won't freak out. We're assuming there's no difference. Now the real reason why I like this is, what if we were trying to prove that it was more than 1 day better? You'd put a 1 here. I've never seen a problem like that given, so don't worry about it. This will always be 0. But that's another reason why I like to write it down. All right, let's go plug them in, see if we can find out how many t-scores that is. So t is equal to 4.2 minus 5.5 over the square root of 1.2 squared over 31 plus 1.5 squared over 30. Go throw that guy into your calculator. You see how many t-scores that is. Got to do a lot of parentheses. It's kind of tricky to get this working. You know, you put one parenthesis in the wrong place, you're going to get a wrong t-score. Did I get a number yet? Forget you got to square these guys. Negative what?
3.7.
It's probably pretty close. 3.7, anybody else get that? Negative 3.7? Is 3.7 0?
Yeah.
3.73? That seems about right. Okay, good job. You got to be able to get that in there. Now we draw a picture of this situation. These are all of the different x bar t minus x bar p's. All these differences. Okay, we're going to assume there's no difference. We got a difference of this, negative 1.3. That's what we got when we did our experiment. That turned out to be 3.73 standard deviations away. What's the next thing that we have to know to go find the p-value? Degrees of freedom, right? All right, we're going to take a class vote. You guys can decide which formula we use. Open your book to the top of page 1. 659. Look at that bad boy. And that is not on our green sheets. You like that one?
No.
All right, we're also allowed to use a little bit more conservative estimate. And the other formula, it's okay if we use it, is the smaller sample size minus 1. Which one are we going with as a group this year? I think that's good too. So the degrees of freedom formula that we're going to use, do I need to actually take a real vote to find out? Take your mind.
I think we should.
Okay. See if we got a quorum. That's the formula we're using for degrees of freedom. So you have it here in test statistic. Smaller n minus 1. So in our problem, degrees of freedom, which one was the smaller sample size? 30. So we go 30 minus 1, so our degrees of freedom is 29. So now we can go calculate that p-value. So go to 29 degrees of freedom on your green sheets. We're looking for 3.73. And remember, these are symmetrical, so positives and negatives are the same. Is it off the chart?
Yeah.
Is it just off the chart? So translation, this p-value is 0.0005. So let's remember what that means. We got to get better at p-value, right? If this pill's not doing anything, let's say I give everybody a placebo. You can't get this. It's impossible almost. Less than 0.00. That is never going to happen. Ever. Translation, the pill did something. It can't be equal. The pill did something. It reduced the average number of days it takes for the cold to get better. So we got our typical 3-sentence conclusion, assuming that the difference in the amount of days it gets to get better is nothing between treatment and placebo. There is this chance of getting a difference of 1.3 days or more. Since our p-value is lower than our alpha level, we're going to reject the null hypothesis. Therefore, we do have statistically significant evidence to say that this treatment reduces the number of days you will have cold symptoms. The pill works beyond a reasonable doubt. Questions? Yeah.
You have to always design an experiment before we do that, or just...
No. I was just trying to tie it together. Remember, you guys learned how to do this before. They're not going to make you do it all this time. But this is how you designed it. Well, that's how we're going to figure out if we got something or not. All right, now what if we were doing a confidence interval? First of all, is 0 going to be in that confidence interval? Spit it out or swallow it or something. Is 0 going to be in your confidence interval? Come on! Is 0, when you create your confidence interval, is 0 going to be one of your solutions?
Yeah.
No way! Our X bar's way out here. Margin of error, it's not, I mean, we just said 0's wrong, didn't we? The difference isn't going to be 0. Alright, so what do we do if we're doing a confidence interval? We still do this. Don't do that. Don't do that. Gotta do all these. And here is how we do the confidence interval. This is going to be our negative 1.3 plus or minus t crit times that standard deviation. So let's think about what this would be. 4.2 minus 5.5. That's the negative 1.3 days we got. Plus or minus, so at 29 degrees of freedom for a 95% confidence interval. 29 degrees of freedom, 95% confidence interval. James, did your brain explode?
Yeah.
There's a lot of stuff. I got you. A lot of stuff we're learning. 2 point something? 2.045, and then this whole monster again. 1.2 squared over 31 plus 1.5 squared over 30. So this is going to be negative 1.3 plus or minus something. You've got to be able to make that work in your calculator. get that margin of error. 2.045 times the square root. 0 will not be in that interval. It's going to come in around 0.6 something or 0.7 something. Your parentheses correctly. .705, I think that's probably about right. Plus or minus 0.705. Notice 0 is not going to be in the interval. And your two-sentence conclusion for that. And you got to be able to get that all in there. Okay. Okay, what's different about today? We've got two totally independent things we're looking at. We want to give one group of people the pill, one group not the pill, and we want to see the difference when we're done and see if that is significant or not. Okay, the big new thing is we've got a whole ugly new formula for how far apart all those differences of the x bars are going to be. All right, I want to show you something. You might have wished I showed you this a little sooner. I don't like to show it sooner. Do you have still the data for number 20 in your calculator from last night? Check out your calculator, see if you still got these. Yeah, you got those guys in your calculator?
Oh, yeah.
All right, now didn't you have to go do a hypothesis test and a confidence interval for this data? Okay. All right. Check this out.
Seriously?
Check this out. Go over to tests and see that second one that says t-test? Hit enter. Okay, if they give you data, we had data for this one, right? So you guys had the data, you put there. If they just gave you the summary statistics like this stuff, you would put stats. Was your null hypothesis equal to 0? So if it was something different, you'd put whatever the null hypothesis is there. Okay. My data was in list 1. I don't know what that means. Okay, now here, did you do a one-sided or a two-sided test? I think this was less than 0, right? Looking at your homework, right? This is number 20, B, I think, or C. Wasn't it? You're trying to prove it's less than 0. Okay. Now let's just cruise on down to calculate. See if you guys got the right answer. Should have got a t-score of negative 2.02. Is that correct? Was your p-value between 2.5 and 5%? Should have been. Now, remember, those charts we have can't do it all. Calculator can. That's the actual p-value, 3.2%. Now, what is different about what you did last night? Nothing. Everything that's on your paper from last night needs to be there, and even the 2.5 to 5%. But is this guy going to save you a little time on the calculations when you guys were entering all those numbers? Now, this was my favorite. Watch this. This is fun. This is really fun. We're going to go to t-test. Let's do a little drop.
Oh my god.
No.
Are you serious? Are you serious? Are you serious?
Isn't that cool? There's the picture we draw all the time.
Oh my. I thought my calculator.
Awesome. Oh, let me show you something else.
Oh my.
Dude, what?
Go down to t interval. Did you guys do a confidence interval last night too? Okay, data. It's in L1. I think you guys were supposed to do a 90% confidence interval for last night's homework. Okay, go down to calculate. There's our interval that you should have from last night. Now, what needs to be different on your page? Nothing is different. Nothing is different. You need to have that t-crit, which they don't show you here. Okay, you have to have the formula on the t. Everything needs to be there. But this guy saved you a little time. In fact, they had the z intervals on there last chapter. Should have probably brought that up.
Yeah, just.
But nothing changed. You have to have that t, like this thing. You gotta go. Oh, this is a different problem. You have to have show that. Okay, so nothing changes. This will either, it will save you time on the calculations part, but nothing else is different.
So then, could we also use that for like?
I know what you're talking about. So let's move on.
That's not.
All right, tonight you got 3 problems. 3 of these guys. Different confidence intervals, hypothesis tests, 2 different